Alrighty, lads and ladies, welcome back to Pre-Calculus, MAC1140, section 008. I need just 1 second to get things configured here, and we can get started. Last time we left off having talked about transformations of graphs, and we covered the bulk of the material. Today, however, we're going to dig just a little bit deeper into transformations because it turns out there's some really beautiful geometry there. And the way that that geometry interacts with the algebra, one is really cool, but also it can be a big time saver for you. So let me, there we go. Get my notes here. Yeah, this is where we left off. All right. I'm gonna turn on the screen share and we're gonna get rolling. So you do have a new homework up, and that homework set is going to be due for you on Tuesday of next week. And I just want to warn you, we're also getting kind of close to our first test. So today we're going to finish 2.6 on transformations of graphs, and we're going to start section 2.7, which is on mechanisms, ways to combine functions. So given two functions, how to match them up to make a third. Part of that section, 2.7, leads us into talking about something called an inverse function, which is maybe not what you might think right away when you hear the word inverse. After we do that, we'll be ready for the first test. So I'll share with you the timeline that I'm thinking of. We're a little bit behind following the syllabus, right? 2.6 and 2.7, those are things that we wanted to talk about last week, but we're really just finishing them up this week. Next week, once we finish one-to-one functions, that's when we'll be ready for the exam. The exam goes through section 2.8. So I'm thinking probably we will finish 2.7 on Thursday, and we may be able to start 2.8 Thursday, but probably we won't finish it until next Tuesday, which means exam 1 likely to be a week from next Tuesday. We could cram it in next Thursday on the 23rd. That's an option, and that would get us back on schedule. But I like the idea of giving you a little bit of time to prepare for the test. I don't really want to rush it. So probably what I'll do is this Thursday, the 16th, I will take a little poll here in class. So make sure you come to class on Thursday, make sure you're paying attention. I'll take a little poll and you guys will be able to choose between getting the exam in next week or pushing it to the following week. There's always a give and take there, right? If I give you more time to prepare for the test, that means between those times, I'll be lecturing on material that's not on the test. That can be a little distracting. The other downside is, of course, if we push this test, that kind of shifts the whole schedule a bit, meaning some later test we'll have less time to prepare for. So pay attention in class on Thursday when I will let you guys vote on the day of your first test, but know that it's coming, right? It's within a week and a half. Okay, that's that. Let's do the thing. This is pen dead, Mac 11. All right, let me find that pen. MAC 1140, this is section 008. That is, of course, pre-cal. And today is the 14th of September, 2021. Ooh, this one sucks too. All right, so today, we're going to first finish section 2.7 on transformations. Sorry, 2.6 on transformations. And then we're going to begin section 2.7, combining functions. So a lot of people have this misconception that what mathematicians do with their time is just like big arithmetic problems or big algebra problems or even big calculus problems. But the truth is really none of that. Mathematicians study structure and logic. We try to deduce theorems from a set of axioms. That's really the job of a mathematician, is to try and see what sort of true statements are logical consequences of a set of foundational beliefs called axioms. One of the big things that's done there is studying algebras of functions. So you may have noticed, as we've talked through section 2.6, these functions are all related to each other, and there's kind of a neat algebra relationship between the graphs of those functions. That's what the transformation section is all about. In 2.7, we're going to start talking about ways to combine functions, meaning perform algebra operations between two functions, like multiplying two functions or adding two functions, that sort of thing. Turns out in this grand scope of like seeking theorems, studying algebras of functions is a big deal. Right, so studying, instead of like thinking of algebra as, the symbols represent numbers and we're going to study functions, that map numbers to numbers, many mathematicians study algebras of functions where the objects in question are functions, the symbols represent functions, and we study maps from one function to another. And that is something you're going to get just the tiniest little taste of when we get into 2.7 and 2.8. And it's very fun. It's something that has a lot of deep meaning in higher mathematics. But before we're able to get there, we need to finish our talk on transformations. So you may recall I gave you 4 basic transformations. I'm not going to rewrite everything here. And the order we want to perform them in are horizontal scalings, horizontal shifts, this come down to vertical scalings, and vertical shifts. And the sort of associated algebra operations with each of these, the horizontal scaling was something like, your function f is equal to the parent function with some number multiplying on the inside. Horizontal shifts, I'm not going to write those out. Vertical scalings, these were your function is equal to some constant multiplying the parent function on the outside. Now we want to look more closely at these guys today. So today we're going to talk about 2 special cases. Of these scalings. Okay, and I think we saw a little bit, specifically what I'm talking about here is where C is negative. These are sometimes called reflections. I think we touched on this just a little bit in class on Tuesday, but we're going to look more deeply at these today. All right, so I'm not going to fill in the things here. These are all in your notes from Tuesday. But I want to remind you that a horizontal scaling is where you multiply on the inside by some constant, and a vertical scaling is where you multiply on the outside by some constant. And in most of the examples we've seen, that constant's been positive. Right? So, your vertical scaling, you think of it as like stretching or shrinking the graph. If C is bigger than 1, it's going to stretch the graph. If C is smaller than 1, it's going to shrink the graph. And it's the other way around for the horizontal scaling. If C is smaller than 1, that's going to stretch you horizontally. If C is bigger than 1, that's going to compress you horizontally. And we saw how to work through all of that. But in the special case where C is negative, these perform a flipping operation. And I think we saw one example of a vertical reflection in class on Tuesday, but I'm not sure we've seen any examples of horizontal reflections. And then it turns out, like I said, when you study functions as algebraic objects in their own right, one of the things algebraists love to do, I'm not an algebraist, but one of the things they love to do is classify things. They love to put, mathematical objects into little boxes and say every object in this box has this property. Turns out that the way functions respond to horizontal scalings where the constant is negative is one of those like boxes, right? It's actually two boxes. We call even and odd. And the even and oddness of a function is determined by how it responds to a horizontal scaling where the constant is -1, right? Which is a horizontal reflection or a reflection over the y-axis. So I don't want to beat around the bush anymore. Let's just do it. Just like when you're studying numbers, like integers, splitting them up into even and odd integers, meaningful thing to do, can be helpful. There is a notion of even and odd for a function. So here's the definition. The function f is called even if, and I'm going to give you two equivalent notions here. The first is going to be an algebra definition, and the other one is going to be a geometry definition. And I'll try to convince you that they really are equivalent. Algebra definition first. So a function f is called even if f of -x is the same as f of x. And if you think about what this is, about what this is saying, this says when you multiply on the inside by a -1, in other words, when you scale the graph horizontally by a factor of -1, it doesn't change. It's still equal to the original function. So like think of this as a transformed version of the function f, and think of this as the original version of the function f. What this equation here says is that the function f is invariant under the particular transformation that's induced by this negative. And what is that transformation? Well, if you multiply on the inside by -1, that's a reflection over the y-axis, a horizontal reflection. So what is this really saying? i.e., the graph of f is unchanged. And the math word for that is invariant under horizontal reflection, which is reflection or flipping over the y-axis. So first, let me get one thing straight. Your homework uses this term like reflection in the x-axis or reflection in the y-axis. It's one, bad use of language, but two, it can be a little bit misleading. A reflection over the y-axis is a horizontal reflection, right? Because the y-axis is a vertical thing. When you flip over it, that means you're flipping side to side. So I encourage you to think of this as horizontal reflection rather than the language the book uses, which is reflection in the y-axis or something like that. So an even function is a function that doesn't care if you flip it over the y-axis or not, doesn't care if you flip it horizontally, it stays the same. Odd functions, a little more complicated. Just a little though. Let's see if I have. So the function f is called odd if the algebra definition here is that f of -x is the same as negative f of x. So here, both of the objects are a transformed graph, a transformed function. This one, f of negative x, just like in the definition of even, is a horizontal reflection. It's a reflection over the y-axis. The right-hand side here, negative f of x, look at that, that's a vertical scaling, right? That's the special case where c is -1. That's a vertical reflection, or a reflection over the x-axis. So geometrically, what this is saying is that reflecting over the y-axis is the same as reflecting over the x-axis. So it's not so much an invariance. This says reflecting the graph of f horizontally or over the y-axis is the same as reflecting vertically, which is over the x-axis. So they're both kind of invariant things, right? They're algebra statements that, when interpreted as transformations, tell you something about graphs looking the same, right? An even function's graph looks the same as the original if you flip it over horizontally, over the y-axis. And an odd function's graph looks the same if you flip it horizontally and vertically, right? A horizontal flip is the same as a vertical flip for an odd function. You may have noticed this as you work through some of those transformation problems, like sometimes a vertical stretch is the same as a horizontal compression, right? Sometimes a vertical scaling of one sort or another is the same as a horizontal scaling of one sort or another. Let me show you a few of these horizontal reflections for a few particular functions, and then we'll start trying to diagnose even and oddness, both algebraically and from the graph. Before I dig into that, though, I really would like to find a better pen. I know I've got a big ass thing of black G2s here somewhere. There it is.
So for the odd functions, you would flip them over both the y and the x-axis?
Yes. So the odd function says when you flip over the y-axis, you get the same thing as if you had flipped over the x-axis. So it's not so much a command as it is a question. It's asking, when you flip like this, do you get the same thing as when you flip like this? If the answer to that question is yes, then the function you're looking at is odd. And similarly, the even function definition there is asking, when you flip over the y-axis, does the thing stay the same? If yes, then the function you're looking at is even.
Okay, thank you.
Yeah, of course. All right, let's look at specific examples. So first, let's just look at a few reflected graphs. Sketch. Let's sketch f of negative x, where f of x is, let's do square root of x. I'll give some space. B, f of x is x cubed. And C, f of x is x to the 4. So I just want to see what this horizontal reflection looks like for a few examples, and then we'll start comparing. The square root of x, we know what that looks like. That's one of our parent functions. So we'll start with the graph of the square root of x, and then we'll reflect it horizontally. And remember, when you're just sketching the graph of one of these parent functions, it doesn't need to be perfect and beautiful, but you should make a few points clear. So we know we're going through 1, 1. And we know we're going through 4, 2. Right? Here's the graph, y equals the square root of x. So y equals f of x, the original guy. So if I want to look at the graph of f of negative x, I need to take this graph here and reflect it horizontally. Remember, the general rule for horizontal scalings to get the graph y equals f of cx, we divide all the x values by c. Right? That was the rule. That's why f of 3x is a compressed version and f of 1/2 x is a stretched version. Well, here, the c is -1. So I'm going to divide all these x values by -1, which is the same as multiplying them all by -1. The net effect, so the y values all stay the same, but every x value gets divided by -1. 0, 0 stays 0, 0. But I'm trying to, everything else is going to get moved around. So when I flip this guy over the y-axis, when I flip him horizontally, he's going to turn into this guy. 0, 0 stays 0, 0. 1, 1 becomes -1, 1. And 4, 2 becomes -4, 2. So this is the graph y equals f of -x, which is the one we wanted. And such a graph would be perfect on a test, right? We've got 3 points clearly labeled on each one, right? The origin here, you don't need to label that. I know that that's 0, 0, but the other points you do need to label. And on a test, usually that's the guideline I give, right? I say, label 3 points clearly, usually when I ask you to sketch a graph. And remember, on the test, you are going to have to do this, right? You're going to have to sketch the graph of the parent function on its own. And then you're going to have to sketch a graph of the transform function. And each of those, you're going to have some points labeled. All right. Any questions about how we're getting this graph from this graph? Any hypotheses about this function? Do we think this function might be even or odd or anything like that?
Is it even?
So remember the question we were trying to answer when we asked that is, does the graph stay the same when we do the horizontal reflection? So is this the same graph as this?
It's even since it stays the same?
I'm sorry, Pierre, could you repeat that? So
you mean stay the same, the shape stay the same, or whether you shift it?
So yeah, no, fair enough, right? Literally has the same points on it. Yeah, is literally the same subset of the XY plane.
Then it's odd.
So if this graph were identical to this graph, they all had the exact same points on them, then f of x would be the same as f of -x. And that would tell us that the function is even. Let's look at this next one. I like what you said there. So let's look at this next one. I think you'll find this a fun example. So the parent function here, x cubed, has this like S-shaped graph. 0, 0, definitely on the graph, right? When you plug in x equals 0, you get 0 out. Some other points on this graph that are fairly easy to plot, 1, 1. And -1, -1. So this guy, if I want to sketch his horizontal reflection, graph y equals f of -x. Same deal, right? I'm flipping the graph over the y-axis. I'm flipping it over horizontally, which means I'm going to divide all the x values by -1, which again is the same as multiplying them all by -1. So this point, if I flip it over, is going to come over here. So let me label -1, +1. There she is. Right, this point flipped over the y-axis comes over here. The origin, 0, 0, flipped over the y-axis, he doesn't change. And this guy, -1, -1, if I flip him over the y-axis, he comes over here. It's +1, -1. So this fellow, after that transformation, looks something like this. Oh, modulo my bad art and bad pen. All right, so here's our horizontally reflected, crudely drawn graph. This and this are not identical. They're not the same, right? Like this guy has some shit in quadrant 1, this guy does not. This guy has some shit in quadrant 3, this guy does not. But imagine I flipped the original graph over vertically instead of horizontally. Do you see that that would be the same as this? So this is an odd function because the horizontal flip is the same as a vertical flip. And we'll look at more specific examples in just a second, like trying to detect oddness. But this is our first example of a function that has a clear parity, has a clear even or oddness. The single word for that is parity, P-A-R-I-T-Y.
Can I ask a question?
Sure, yeah, of course.
So for the even functions, the points are still the same. It's just that the x-axis changed from positive to negative, right? And then on
so let me be clear here. This is not an even function, right? This function does not show that symmetry. For an even function or an odd function, what we need is the graphs of whatever type to match exactly. So when we reflect, if this reflection over the y-axis left me with the exact same graph, then that would be an even function. So I think I like where your question is going. Let me ask you to hold on to it for just 1 second while we do this last one, and then we can approach that, I think, a little better.
Okay, so A was odd too, though, you said?
No, neither. A is neither even nor odd.
Oh, okay.
This one happens to be odd, but don't worry about that for now, right? The point of this example is just to practice sketching the horizontal reflection. That's all we're worried about here.
Okay.
We'll worry about answering even and odd in a second. So the graph of x to the 4, remember, looks a lot like the graph of x squared. It's just kind of flatter on the bottom. Something like this. 0, 0 is here. It's true that 1, 1 is here. And that -1, 1 is here. Those are some points that are on that graph. And if I reflect this guy horizontally, this will be an example of an even function. This is actually invariant under that flip. Because you see this point right here, 1, 1, if I flip him over, he's going to become this point right here, -1, 1. And this point right here, -1, 1, if I flip him over, is going to become this point. So this is an example of a function that is actually invariant under that flip, right? The graph we get out after flipping is literally identical to the graph we started with. This is an even function. So the only example here that has that property of an even function is the last one, because when I flip this guy over the y-axis, he don't change at all. It's the exact same thing. But the guy in part B does have some symmetry, and we'll look at that in just a second. Okay. Let's sketch a couple vertical reflections. I'll just do 2 of these. And we'll do x cubed again. Okay, I do see a question in chat about the test. We talked about it at the start of the class, but we're going to take a vote on Thursday for the exact day of the first test. I think there's so there's a few interesting questions in the chat I'd like to address. Even exponents stay the same. So if you have a polynomial and all the powers of x are even, that will end up being an even function. Turns out that's part of the reason we call it even. The other question is this, does it mean that all parabolas are even functions? Not necessarily. All parabolas whose vertex lives along the y-axis, those would all be even functions. But if you shift that parabola left or right, then all of a sudden reflecting it over the y-axis does start to do things. Doesn't necessarily stay the same. So any parabola whose vertex lives along the y-axis will be an even function as well. And you'll see that that's actually equivalent to the answer to the previous question. But let's take a look at these guys real quick. If I start with the absolute value function, whose graph we know, it's this V shape. Slope over there is +1, slope over here is, slope over there is -1, slope over here is +1. Some points on the graph. You notice there's a lot of graphs that share the same trio of points, 0, 0, 1, 1, -1, 1. This time we're looking for the negative of f of x. That means we're doing a vertical flip. We're flipping over the x-axis. That's going to get me something that looks like this. Things like this will happen as you draw graphs where like, oh, that didn't, my pen slipped or whatever. It doesn't look as beautiful as it should. That's okay. That's why we label points. So this right here is 1, -1. This over here is -1, -1. So that's what flipping this guy over the x-axis looks like. Right? That's what a vertical flip here looks like. And 0, 0 is still there, of course. x cubed, this is going to be the fun one to look at here. Again, that parent function, we know. Oh, just cannot draw today. X cubed on its own looks something like this. 0, 1, negative 1 on the graph. And when I flip him over vertically, see, it's not that it's the same operation as a horizontal flip, it's a different operation. Instead of sending this point over to here, I'm going to send this point down to here. So 0, 0 is going to stay where it was. 1, 1, this point is going to get sent down here to 1, negative 1. And this guy, negative 1, is going to get flipped up here to negative 1, positive 1. And the result looks like this. And then the thing to notice about this last guy the graph of negative f of x is the same to the one we did earlier, that horizontal reflection, which, remind you real quick, if I were to reflect this horizontally, flipping this over like that, this point goes over here, that whole branch comes over here. This point goes over here, and this whole branch comes over here. You see, these are the same. Right? So this is the graph of f of negative x, and this is the graph of negative f of x, and they're literally the same. And that tells us that f of x equals x cubed is an odd function. So even functions don't care when you flip them over horizontally. They stay exactly the same. Odd functions, if you flip them horizontally, it's the same as flipping them vertically. Now, both of those statements can be rephrased in terms of a symmetry of the original graph. You don't need to do both of these transformations every time you want to check if a function is odd. Yeah, and Victoria's comment in the chat there is precisely what we were saying, right? That this guy, when we flip him over vertically, is the same as the guy we did before, where we flipped that same graph x cubed over horizontally. And if you look back at the definition of an odd function, that's precisely what it means to be an odd function, right? That flipping vertically is the same as flipping horizontally. The absolute value function here definitely doesn't stay the same when we flip him vertically. But do you see any symmetry here? What would happen if I flip this horizontally? What kind of function is this?
The same?
Yeah, if I were to flip this guy over the y-axis, if I were to flip him over horizontally, he would stay the same, right? So this is an even function. Let's write down what we're saying. So detecting even and odd functions how to know if your function is even or odd. The graph of an even function, we said it doesn't change when you reflect over the y-axis. Well, that means it's symmetric about the y-axis. Or the vertical axis, if you've got, if it's some other variable that you're labeling your vertical axis as, it's symmetric about that. So if I have a function that does something like this over here, and does that exact same thing over here, graph that is symmetric about the y-axis, that is the graph of an even function. And you can see this a bunch of ways. If you take your favorite x value, you look at this point, the y value there, this is x comma f of x. And you look at a symmetric x value, like over here, same distance, just going off to the left. This would be the negative of that x, right? Like if this is 3, this is -3. If this is 5, this is -5. This is the point, negative x comma f of negative x. And since they are at the same height, their y values must be equal. In other words, f of negative x is the same as f of x, which was our definition. So if you want to know if your function is even or odd, and you have the graph, you can tell if the function is even by asking, is it symmetric about the y-axis? If I were to fold this up, would it sit right on top of itself? If the answer to that question is yes, then you've got yourself an even function. So graph of an even function always symmetric about the y-axis. The graph of an odd function also exhibits some symmetry. But this time it's symmetric, not about one of the axes, but about the origin. And I'll show you exactly what I mean. What that means is you have a graph. Let me take some nice example of an odd function. Like this. Okay, let's say something like that. This is an example of an odd function. And what we mean by origin symmetry is that if you take any x value on this graph, like maybe over here, and you reflect that point through the origin, you will land over here at another point on the graph whose x value is the negative of that one. So this over here, this would be the point x comma f of x. And this point over here is negative x comma f of negative x. And the y value here, f of x, is the same size as the y value over here, but it's in the opposite direction. I'll run out of colors here. This y value, f of x, is the same size as this y value, f of negative x, all right? But they're in opposite directions. So here, f of negative x, it's not exactly the same as f of x, it's the negative of f of x. So if this point right here is like 3 comma 2, then this point over here would be like negative 3 comma negative 2. That's origin symmetry. So if you have the graph of your function, you can answer the question, is this even or is this odd? Pretty easily, just by checking for these symmetries. And it needs to be true everywhere, not just at one point, but the whole graph needs to have this symmetry. All right, just having one point that reflects cleanly over here to another point doesn't make that function even. It's the fact that every point over here reflects across the y-axis to a point over here. And similarly, every point over here reflects through the origin to a point over here, right? Like this point would reflect through the origin to this point. Not too bad, right? So some comments. Not every function is even or odd. Functions can be even, odd, or neither. That's one comment. Another comment. This symmetry stuff is useful only if we have the graph. Right? I can't use a symmetry argument to say this is an even function or this is an odd function if I don't have the graph of the function to begin with. So we'd really like to resolve that second comment. It would be nice if there was a way to say whether a function is even or odd without having the graph. In fact, knowing whether a function is even or odd is one of those things that can make graphing them easier. There's a remark in chat that I want to address. So is the origin always 0? Yeah, the origin is by definition the ordered pair is 0, 0. When I say the origin, that's just a name for the point 0, 0. So the origin on this graph is here. The origin on this graph is here. All right. So, question. Can we tell if a function is even, odd, or neither without having the graph? Because like, imagine you want to graph a function and you know that it's odd. And you make a big table and eventually you get this part of the graph. It was a lot of work. And you maybe don't want to make another table to try and find the other piece of the graph, but you know the function is odd for whatever reason. Well, if you know what the graph looks like over here, and you know that the function is odd, you can draw this part of the graph without any work at all, because you know it has to have this symmetry. So once you have one part of the graph, either the part to the right of the y-axis or the part to the left of the y-axis, if you know the function is odd, you can draw the other part. The same thing's true if the function's even, right? If I just have this part of the function's graph and I know that the function is even, then I automatically know what this part of the graph looks like. I can draw it without making a table or doing any additional work. So one of the real utilities of even and odd functions is that it's a time saver, right? When it comes to drawing a graph, if you know the function is even, then you only have to draw half the graph. The other half comes for free because of that symmetry. Same is true for odd functions. So we love a good answer to this question. Can we tell if a function is even, odd, or neither without having the graph, and then use that? A graph of a function that is neither even nor odd is just one that lacks these symmetries. So let's, it's a good question. We can explore it a little bit. Let's try classifying some curves as even, odd, or neither, just based on the graph. Okay, let's do it. Looking at this first guy. Yeah, so Genesis question there, can you determine if the function is even, odd, or neither algebraically? The answer is yes, and that's what we're gonna do right after this, but I wanted to address Chris's question. So even, odd, or neither? Does this function's graph exhibit any of those symmetries?
Odd.
Odd.
Very good, this is an odd function. If you take a point on this graph, say anywhere, but for example, over here, and you reflect that thing through the origin, you're gonna get another point on that graph. Origin symmetry implies that this function, which I've called f of x, f, is an odd function. What about in B?
Looks like it'd be neither.
Yeah, this one is neither, right? We have neither origin nor y-axis symmetry. So this function g is neither even nor. Someone knocking on my door. 10 seconds. Okay, very sorry about that, guys. Some roofer just showed up and said he wanted to offer his services. Fucking. All right. So yeah, this graph exhibits neither of those symmetries, right? There's no piece to the right of the y-axis that looks like this, right? There's nothing like this going on over here. This guy is not symmetric about the y-axis. Definitely, if you reflect a point over here through the origin, there's nothing up here, right? And similarly, if I take a point like down here and reflect it over the y-axis, there's nothing over here. So yeah, he exhibits neither of those symmetries. So he's neither even nor odd. And the last guy?
It would be even.
Good, yeah, this is an even function. Take a point over here, reflect across the y-axis, I get a point over here. So this has y-axis symmetry, which implies this function, which I've called h, is an even function. All right. So if you got the graph, it's not too bad. But absent the graph, how do we do it? The answer to that question is foreshadowed by Genesis' question algebraically. There's an algebra class, right? We're gonna do it with algebra. So without the graph, answer to the question from the previous page. Yes, using algebra. And the definition. We can tell if a function is even or neither. Right, what does the definition say? Well, the definition says f of negative x equals f of x, or f of negative x equals negative f of x. We know what those things are, right? If you give me the algebra definition of the function f, I can find f of negative x. That's something that was in your first homework set, right? Where you replace x by negative x, and you simplify and see if it turns into either of those things. So to investigate parity, and remember this word parity is even or odd or neither, right? That's what parity means. We write down f of negative x and see if it can be simplified into the original f of x, the vertical flip version, negative f of x, or neither of those. And the result is what you'd think it is. If f of negative x can be simplified to f of x, that means f of negative x equals f of x. So that's an even function. If f of negative x can be simplified to the negative of f of x, well, that means f of negative x is negative f of x, which means you're looking at an odd function. And if this can't be simplified into either of those, then it's neither. Let's do it. So we're going to determine algebraically the parity of a few functions. We'll start with f of x equals x to the fifth plus x. Then we'll do g of x equals 1 minus x to the 4. Let's get a couple more of these in here. How about h of x equals x over 1 plus x squared. E of x equals 2x minus x squared. Okay, so you got plenty of stuff to do here. The game for each of these is to look at f of negative x, or g of negative x, h of negative x, e of negative x. We're going to plug in negative x and see if it simplifies to the original or the negated version. Let's do part A. What is f of negative x? How do I find it?
Plug in negative x for your x values.
Yeah, everywhere there's an x in this expression, I'm going to swap it with parentheses negative x. So instead of x to the 5, I have parentheses negative x to the 5. Plus, instead of x, I have parentheses negative x. The negative of x to the 5, there's something up here. The negative of x to the 5th power, that's negative x times negative x times negative x times negative x times, one more, right? 1, 2, 3, 4, negative x. So I've got negative times negative here. That's positive. So this is these two pieces give me x squared. Positive x squared, right? Negative times negative is positive. Times these two pieces, same thing, right? Negative x times negative x, that's positive x squared. And then this last guy, negative x, is just negative x. X squared times x squared, that's x to the 4 times negative x. And now there's just one negative, right? I've got a positive times a negative. The x times x gives me x to the 5. This is negative x to the 5th without the parentheses. And there's nothing sacred about 5 here. I want to be clear about that. In fact, I want to ask you about that. What is it about this 5 that made this negative pop out?
It's odd.
Right. It's the parity of the power itself. The fact that there was an odd number of negative x's here guaranteed that I'd be able to pair them up into x squareds and then have one left over. That's what being odd means, right? It means it's one more than a multiple of 2. So in general, negative x raised to an odd power is the same as the negative of x raised to that same odd power. And you may have guessed, negative x raised to an even power is the same as just x raised to that same even power. So odd powers spit out negatives, even powers gobble them up. Okay, with that in mind, this negative x to the 5 is negative x to the 5 like that. And then plus negative x is the same as just minus x, right? If you add negative 3, that's the same as subtracting 3. Okay, I found f of negative x. It's looking pretty simplified. I don't see anything else I can do, at least not right away. But it doesn't look like this. So probably not an even function. Remember what our goal is. We're trying to see if it can be simplified either to the original or to the original with a negative out front. I don't think this is going to happen here, right? This thing looking pretty different from this thing. But I think we have a hope of this. Does anybody see a way I could turn this expression into the negative of the original? What algebra step would make that clear?
You take out the factor of -1.
Excellent. Yeah, John nailed it. We can factor out a -1. We can factor this negative. This becomes negative, parentheses, x to the 5 plus x. And now that x to the 5 plus x, that's my original. This is negative f of x. So f is odd. Everybody see that? We've just shown algebraically that this function is an odd function because when you swap in a negative x, after some algebra finagling, you're able to pop the negative out and you have the original left over, right? Right here, this is negative and this is f of x. So it's negative f of x. And it's the same as f of negative x. All right, let's do part B. I won't be as slow pokey with the details this time. The function name here is g, so not f, but we're going to do the same thing. We're going to look at g of negative x and see if that simplifies to either the original or the negative g. G of negative x. Well, g of x is 1 minus x to the 4th. So this is 1 minus negative x in parentheses to the 4th. The parentheses here are hugely important, right? It's how you handle the parens that determines everything. Now we said a second ago that if you take negative x and raise it to an even power, you're just going to get x raised to that same even power. Negative x to the 4 is just x to the 4. And wouldn't you know, this is the original function. This is g of x. So g is even. We might be able to squeeze h in here, but let's be generous to ourselves. Let's give ourselves some space. For the function h, we do the same thing. We're going to look at h of negative x and see if that can be simplified to anything nice. Same procedure. Everywhere there's an x, we write negative x in parentheses. So this is negative x over 1 plus negative x squared. Upstairs there, this negative x, there's no power here, there's no constant here, there's nothing else going on upstairs besides the negative x, so I can get rid of that parentheses. Downstairs here, 1 is just 1 plus, and then negative x squared, that's negative x to an even power, so it's the same as just x squared. And then the last sort of thing to notice here is that you can pop the negative out from the top. This is the same as negative x over 1 plus x squared. Like negative 3 over 2 is the same as negative out front and then 3 over 2. Right? Really is the same. So this is negative h of x. And I think the only step there that deserves any little help is that negative a divided by b, this is really the same thing as negative of a over b. And if you want, and this could also be written as a over negative b, just for the curious, right? So here we're just using that to take this negative from this x and pop it out front. And then, oh, look at that, this is h of x. So this is negative h of x. All right, last one. If I take this function e and I swap x for negative x, that's going to be 2 times negative x minus negative x squared. Which is negative 2x minus regular old x squared, just following that same rule. And this guy, try as we might, we can like factor out a negative, and then this would become 2x plus x squared. This looks like neither the original function nor the negative of the original function. So E is neither even nor odd. I didn't write it down up here. This so H is odd. Sorry. So the function H is an odd function because when we plug in negative x, we're able to force that negative out and have the original left over. The last guy there, E, is neither even nor odd because no matter how we try, I cannot turn this into the negative of the original, 2x minus x squared, nor can I turn it into the original itself. So that's how you detect using algebra if a function is even or odd. And it's not too bad. This is something that I may ask you to do on the first test. It's a pretty classic, pretty standard problem. You know, prove algebraically that such and such function is even or such and such function is odd. Alrighty, that's the end of this section, section 2.6, a discussion of even and odd functions. Later in your math careers, you'll be doing things like finding the area under a curve. And if you know that that curve is an even function, then you can save yourself a shitload of time because you know there's a lot of symmetry. Or you'll be finding things like tangent lines to a curve. Same idea there is if you have some information about one point, you can get information about other points, making these symmetry arguments. And those are huge, huge time savers. I remember the first time I taught Calc 2 here at Santa Fe, I was a little bit cruel on their first exam. I gave them an area problem. It's called an integral. And if you recognize that the thing you're dealing with was an odd function, then it's a one-line problem. You just write down the answer is 0. If you don't, then it's a considerably harder problem. And not a whole lot of people caught that. And I don't try to trick people like that anymore. Looking back, that wasn't very nice. But it's one of those things that shows up in real life. It shows up all the time. And anytime you can make a symmetry argument to simplify your problem, you should. Megan asks, will there be a review day before the exam? Probably not a review day, right? I don't want to burn a whole day of class on the review, but I will post another quiz, and I'll post some resources, places you can go for more practice problems, things like that. And then if you want to bring any of those to office hours or something like that, we can certainly work together a little bit to review, but there won't be a full review day. All right, in the last few minutes here, we are just about out of time, aren't we? I guess we're gonna have to stop there for now, which means, shit. So your homework does have you going into 2.7. I have this set to be due for you next Thursday. Yeah, so you'll actually be up 14th, 14th. I have this set to do on the 21st. All right, yeah, never mind, you'll be fine. All right, I'm gonna leave it there for today then, guys. Next time we're gonna talk about combining functions, one-to-one functions, inverses. Remember, make sure you come to class on Thursday because that's when we're going to be setting the exact date for the next test. So please don't forget to do that. That's it, take care.